Hello, my name is Vinay Narayane. I am pursuing my PhD studies under the supervision of Professor Girish Kumar, and the topic of today's discussion is microwave mixers. Microwave mixers or mixers in general is a very vital component in the RX and TX, which is the receiver and transmitter chain of any communication system. So, be it GSM, be it mobile communication, be it satellite communication, mixers are very vital components. So, we are going to study these mixers in the upcoming slides and in this lecture henceforth. So, let us begin. Let us take an example of an RX receiver chain where we have an antenna which receives the signal, and we have an RF amplifier which amplifies the signal. Then we have a channel select filter, and the signal is further processed using amplifier, demodulator, and then finally given to a display or a speaker. Now, let us take a case of a GSM mobile system where the incoming signal is at a frequency of 900 megahertz and the channel select filter requires a bandwidth of 200 kilohertz. Now, to achieve this bandwidth at this particular frequency, we require a Q of about 4500, which is like very big and impossible to achieve at such a higher frequency. If now we convert this incoming signal of 900 megahertz to a lower frequency value or an intermediate frequency value, let us say of 76.8 megahertz, we get a Q requirement of the filter to be 384, which is still high, but can be accomplished or can be achieved, and it is low compared to the 4500 value in earlier case. So, the point here is it is difficult to process the signal at very high frequency, and hence we have to convert this high frequency signal into a lower frequency value, and that is why we need a block in between the RF amplifier and the channel select filter, and that block is nothing but mixer. So, mixer is nothing but a frequency translation device which translates a frequency from one value to another, or it translates a signal from one frequency to another. This is the fundamental operation and need of a mixer. We are going to study mixers in three parts. In first part, we will study the fundamentals of a mixer. We will study mixer as a circuit component, what are the input output signals, and in the second part, we are going to study the devices and circuits which are commonly used to implement a mixer. In the third part, we are going to study some of the design considerations using an example. Let us begin. So, mixer has three ports. You have an RF port, an LO port, and an IF port. RF stands for radio frequency, LO is the local oscillator, IF is intermediate frequency. RF and LO are typically high frequency ports, whereas IF is a low or intermediate frequency port. The RF port and IF port can be used both as input and output ports depending on the application, while the LO port is always the input port. Now, let us see a basic operation of a mixer. If we have two frequencies at the input of the mixer, F1 and F2, which are given in the spectral form here. So, we have an F1 signal which is a band limited signal, and we have a local oscillator which is at a frequency F2. Then the mixer output is like this. So, ideally with two frequencies input, the mixer produces the sum and the difference frequency. So, at the mixer output we should get F2 plus F1 and F2 minus F1 ideally. So, depending on the application, we either choose one of these sidebands. So, this is called as the lower sideband and this is called as the upper sideband. So, there are two kinds of mixer depending on which frequency signal that we choose at the output, and they are up conversion mixer and down conversion mixer. In case of up conversion mixer, the input signal is given at the IF port. The signal at the IF port mixes with the signal at the LO port, and these mixing signals produce the sum and the difference frequencies, and in this case we choose the sum frequency which is the RF frequency. So, FRF is equal to FLO plus FIF. In case of down conversion mixer, the input is at the RF port and this signal at the input RF port mixes with the signal at the LO, and these two signals after mixing with each other produces the sum and the difference frequency, and we choose the difference frequency in this case, which is output at the IF port. So, FIF is equal to FLO minus FRF. This is the basic operation of a mixer in up conversion and down conversion case. Now, let us take an example of a down conversion mixer. Let us say that we have an incoming frequency at the RF band which is equal to 900 megahertz, and the IF desired is 76.8 megahertz, and the question is, what is the LO frequency that is required to produce this conversion? Simple, we have a formula, FLO is equal to FRF plus or minus FIF using the basic mixer operation. Now, if I choose the plus sign here, I get the local oscillator frequency to be 900 plus 76.8, which is equal to 976.8 megahertz. Now, since I have chosen the plus sign and the local oscillator frequency is higher than the incoming RF frequency, such kind of down conversion is called as super heterodyne down conversion. We must have known this or heard this term quite a bit of time, and the super in this case indicate that the local oscillator frequency is greater than the RF frequency. Let us take an interesting case here. Now, in the RF at the input of the mixer, we have another frequency which is at 1053.6 megahertz. This frequency along with the desired RF which is at 900 megahertz mixes with the LO frequency which is 976.8 megahertz, and the mixing between this frequency and this frequency, if you see, produces the same IF output. In the frequency domain, if you see the spectrum, you have the local oscillator at this frequency, you have the desired RF band, and this is the special frequency that we are talking about, and after conversion both these signals mix with the LO and they produce the same IF output. So, basically if you see, this kind of operation is really not desired. This is a mixing or scrambling of the desired signal and should be avoided. So, this frequency is called as the image frequency, and it has to be removed. There are ways to remove this image frequency or to nullify the effect, and it can be achieved using two ways. One is you can have a image reject filter in the RF path so that you do not allow this frequency to come into the mixer, and second is you use an image reject mixer, which is a configuration that we will discuss in later part of this course. So, image frequency is very important. It has to be considered and should be avoided to enter the mixer. Now, the question is how is this implemented, the basic operation. So, we have two signals with frequency omega 1 and omega 2 sinusoidally varying signals, and the question is what operation do I perform on these signals to get the output signal which contains the sum and the difference frequency. So, it is simple. If we just multiply these two incoming signals, that is I multiply A1 cos omega 1 t into A2 cos omega 2 t by using basic trigonometric relations, we get an output which contains the difference and the sum component of the frequencies. So, mixer is inherently or basically is a multiplier, and that is why in the symbol of the mixer, if you have noticed, we represent it using a multiplication symbol. Okay, so how is this multiplication achieved in the real world? What devices or what techniques we use to achieve the multiplication physically? So, there are two techniques. In first, we use a non-linear transfer function system, and in the second we use a switching device which is nothing but a linear time variant system. So, in the first case, we have a system which has a non-linear transfer function, and at the input of this system, if I give a two-tone signal, a tone meaning a frequency, if I have a two-tone signal input to this particular nonlinear system, I get at the output the difference and the sum frequencies. Similarly, in case of switching devices, if I have a linear time variant system and at the input of this system, if I have two-tone signal with two different frequencies, at the output I can get the difference and the sum frequencies. So, these are the two techniques which are used to analyze the operation of a mixer and to implement mixers. So, inherently these two techniques are the same, but just the way of analysis is different, although we study both these techniques in detail in upcoming slides. So, let us take the case of mixer implementation using non-linearity. So here you can see we have a non-linear device, and we know that it can be a diode or a BJT. At the input we have a signal Vi, and the output we have a current which is I0. Now we know that the diode current and voltage relation, so the output current varies exponentially with the input voltage. And if I expand this particular expression using a Taylor series, what I get is this expression. If you observe, the output current here depends not only linearly on the input, but also it contains the square of the input, the cube of the input, and so on. So this is the non-linearity which we require to achieve the mixing action. Now the Vi is nothing but sum of two input signals V1 of t, V2 of t, which are at two different frequencies, omega 1 and omega 2. If I substitute this expression into this particular equation and I solve it, analyze it, I get the following terms. Now this particular expression that is being written here is taken by considering only the second order term. The third order term is not considered in this particular expression, but you can always solve it and see what are the frequency terms which are generated because of the cubic term. Okay, so let's analyze this output in terms of frequencies that it contains. So first you have an I0, which is the DC component, you have the input frequencies, you also have the second harmonics of these input frequencies along with the DC signal, and you have the desired mixing, which is omega 1 t into omega 2. So cos of omega 1 t into cos of omega 2 t, which will in turn produce omega 1 minus omega 2 and omega 1 plus omega 2. So the desired mixing component is, of course, should be chosen by using appropriate filtering. So you see that by using a nonlinear device, in actual you get a lot of different frequency components at the output of a mixer along with the desired output. So this is how a mixer is implemented using a nonlinear transfer function device. Let's take the second case where we have mixer implementation using a switching device. So in this case you have an input sinusoidal signal V1, which is given to the output through a switch which is controlled by the second signal V2, which is typically a square wave ranging from 0 to 1. So the input is switched to the output using a control signal V2. So simply Vout is nothing but V1 when the switch is on, and it's equal to 0 when the switch is off. Mathematically we can write it as Vout is equal to V1 of t into V2 of t. This is because the switch on condition is achieved when the V2 is 1 and switch off condition is achieved when V2 is 0. So Vout is equal to V1 of t into V2 of t, and if these two signals are at two different frequencies, we achieve what we desire, which is the mixing. So if V1 is at omega 1, V2 is at omega 2, I multiply these two signals and at the output I should get Vout containing the desired mixing. But there is a discrepancy that this is a square wave and it cannot contain just the omega 2 term here, just a single frequency. It has to contain the odd harmonics of this frequency as well. So in conclusion, in the Vout we contain the desired mixing, which is cos omega 1 t into cos omega 2 t, along with the harmonic mixing, which is omega 1 mixing with thrice omega 2, omega 1 mixing with 5 omega 2, and so on. And of course you have to filter the desired mixing signal using appropriate filtering. So the switch which we mentioned here, or the switch that we discussed here, can be implemented using a diode or a FET or any kind of transistor. So let's review the basic mixer operation again. We have a mixer. We have a mixer here. At the input RF port, I have a signal at omega 1. At the LO input, local oscillator input, I have a signal at omega 2. And the corrugated line that you see here is nothing but the noise floor present at both these inputs. And ideally, the mixer should produce the sum and the difference of these two frequencies. But as we just saw, when we implement a mixer using various physical devices, the mixer output contains lot more than desired, or there are various undesired products that are present at the mixer output. So let's see, when I turn on this mixer, what are the frequencies and components that are produced at the mixer output. So this is what happens when the mixer is turned on. The desired signals were just omega 2 minus omega 1 and omega 2 plus omega 1, but you see that there is a lot of changes that have happened in this process. Now take a moment, you can pause the video and observe what has happened. So I'll just flash it again. So you have a mixer, you have two signals, and ideally you should produce the sum and the difference, but this is what happens when you turn on the mixer. Now note down the observations, what are the things that have changed when the mixer was turned on, and you will notice several things which are called as mixer non-idealities, and these mixer non-idealities have to be measured using some parameters. These parameters are called as mixer performance metrics or mixer specifications. So let's go one by one. First observation, you have an input RF signal at some level, but the output IF is at a certain different amplitude level, and this difference is called as the conversion gain or loss. So in this particular case, I have shown an amplification, so you have a conversion gain, but in some cases you can also have a conversion loss. So this is one of the important specification of a mixer. Of course, it's not a non-ideality, but it's a specification that a mixer has. It's a performance matrix that should be specified when you mention about a mixer. Second thing, if you have noticed, there are certain things which are appearing at the input ports as well. So after the mixer was turned on, I get the omega 2, which is local oscillator frequency, coming at the RF frequency, and the RF frequency coming at the LO port, and also I have omega 1, omega 2 at the IF output. So these are called as port leakages or signal leaking from one port to another, and the mixer specification or mixer performance matrix related to this is called as port to port isolation. So it's very important that these leakages should be minimized to a level as low as possible. The third thing that you might have noticed is the noise floor. If you see the noise floor level here, and if you see the noise floor level at the output, it is certainly raised, right? So the mixer is adding certain amount of noise in the process, and this noise addition is measured using a noise figure metric, which is familiar to us. We know what is a noise figure. Mixer, being a nonlinear device, also has a noise figure associated with it. Next, we observe there are various terms, for example, twice omega 1 minus omega 2, twice omega 2 twice omega 2 minus omega 1, and the coding here, if you have noticed, is nothing but the first number represents the multiplication of omega 1, the second number represents the multiplication of omega 2. So it's like one integer multiplier here, second integer multiplier here. So this is minus 1 1. This frequency component is 2 minus 1, this component is minus 1 2, this component is 1 1, and so on. So this is the coding which we will see later, how general mixer equation is represented, and these signals are again not desired. These unwanted signals arise because of the non-linearity present in the mixing device, and these are called as the intermodulation products, and this non-linearity is measured using a performance matrix called as linearity. So we say a mixer is more linear if these frequency components generated at the mixer output are very low compared to the IF output. So linearity is a very important factor or very important performance matrix while specifying a mixer. Next, we see these minus 4 3, minus 2 3 components which are arising in the mixer output, and these are called as spurious responses. These arise because multiple harmonics of the incoming signal, which is RF signal, and harmonic of LO signal mix with each other, and they produce something which is not desired. Now you might wonder that we are anyway filtering the output, so all these things can be filtered out, but the thing to be worried here is this: if you observe, the intermodulation product arising because of the non-linearity and because of the spurious response are very close to the desired IF output. So, even if I put a filter over here, I cannot reduce these particular components beyond a certain level, and they might cause IF output to be degraded. So, let us see all these specifications one by one in detail in upcoming slides. So, before going to the conversion gain, let us first discuss about the operating frequency range of a mixer, and it depends on the devices, which are nothing but diodes and transistors that are used while building the mixer, and also depends on other components that have been used to build the mixer circuit. Conversion gain, very simple, it is defined as the output power in one of the side bands, which is the IF output power divided by the RF input power. In dB, it is simply the difference between the IF power and the RF power in dBm. Now, while defining conversion gain using this expression, we have assumed that the matching has been taken care of. So, this expression does not account for any mismatch losses, but in literature you might see that the conversion gain expression or conversion gain number also includes the mismatch losses. Okay. Next is the port to port isolation. We have signal leaking from the LO port to the RF and IF port. We have signal leaking from the RF port to the LO and IF port, and so on. So, the important one are the LO RF and LO IF isolations, which are more significant, and we will see that why these are more significant as compared to RF IF isolation. So, let us first consider the case that you have inadequate LO to RF isolation, which means that a considerable amount of signal from the LO port leaks into the RF port. And one thing that I want to mention, which we will see later, is that the LO signal has a higher amplitude than the RF signal. Now, before the mixer, we have an LNA and an antenna connected to it. So, let us say that the LO signal leaks into the LNA output, and this will result in a poor dynamic range of the LNA. So, this will reduce the dynamic range of the LNA, and if LNA has a non-zero S12 value, the signal will further go to the antenna, and this will cause interference to other communication channels. In worst case, in case of defense application, this leakage of LO signal through antenna might enable your enemy to locate your receiver. Let us take a case of inadequate LO to IF isolation, where a considerable amount of LO power leaks into the IF port, and after the mixer, after the IF port, we typically have an IF amplifier, and if the signal leaks into the IF amplifier, it might end up saturating this amplifier, and hence you might require a very sharp filter to reject the LO leakage going into the IF amplifier. So, these are the things which have to be considered, and it is very important to have a good port to port isolation numbers for a mixer. We have a noise figure to be considered for a mixer. We know that noise figure is defined as SNR in by SNR out, and the noise figure basically tells you how much noise is being added by the mixer to the input signal. So, the noise added not only depend on the mixer devices and components, but it also arises because of the conversion process, and we will study this using a simple example. So, there are two types of noise figure specification. One is an SSB, which is single sideband noise figure, other is a DSB, which is double sideband noise figure. So, in case of SSB, as you can see here, the RF signal, which is the band limited signal, is present only on one side of the LO. So, this image noise which is present at this particular frequency folds back after the conversion onto the same IF output. So, as you can see here, you have an in-band noise, plus on top of it you have a image noise setting after the conversion process. Whereas, in case of double sideband mixers, where you have the local oscillator frequency and the RF is present on both sides of this frequency, after mixing conversion you do not have the image noise addition, it is just the in-band noise that is present in the mixer output, and hence we see that the SSB noise figure is twice that of the DSB noise figure. or SMPS noise figure is 3 dB higher than the DSB noise figure. This is a very important point to be considered while discussing mixer noise figures. Next we will see linearity, very important. Although a mixer is implemented using a non-linear device, the mixer has to perform linearly, which means that the output signal has to change linearly with the changes in the input signal, and this will happen as long as the input signal is very small compared to the LO signal. But the question is how small, and how small is measured using two specifications. One is 1 dB compression point and another is IP3 point, which is called as third order intercept. We will see this later. First we will see what is a 1 dB compression point. So let us focus on this graph. We have an IF output on the y axis and we have an RF input power on the x axis. As I increase the RF input power, IF output power also increases linearly only up to a certain point of RF input level. So after this point, if I keep increasing my RF input power, my IF output power starts saturating. It does not vary linearly, and the value of the input RF signal level at which the difference between the actual IF power and the desired IF power is 1 dB is called as the input 1 dB compression point. So this is a very important specification. Higher is this point, better is the linearity, better is the mixer. Next we will see the intermodulation distortion, which is measured using IP3 point. So the system is, you have a mixer, at the input you give two tone equal amplitude signal represented like this here, RF1, RF2, and you have a local oscillator, and what happens is these two signals mix with the LO to produce the desired outputs along with certain spurious signals. So this level of spurious signals become equal to the desired output at a certain input power level of these two signals, which is explained using this graph. Let us say you have an output power on the y axis and you have an RF input power on the x axis. This is the desired IF output, which is this, and you see this line which has a slope thrice that of this line is nothing but the graph of these intermodulation products. So the point or the input power level at which these two signals have equal amplitude is called as input third order intercept point, or IIP3. Now this point is not an actual point, it cannot be measured. Instead what we do is we measure the linear output, IF output, we measure the 3 points on the IMD, which is intermodulation distortion, we extrapolate these two lines and we see that the intersection is given by the IP3 point. It is very important specification. Higher is the IP3 point, better is the mixer. And lastly we will consider the spurious response. So a mixer general equation is given as this. So you have IF output arises due to MFRF plus NFLO, where M and N are integers, they can take positive as well as negative values, and this becomes important because let us say normally we have M equal to 1 or minus 1 and N equal to 1 or minus 1, but if you have a strong RF interference signal at the input of the mixer, it might happen that the higher harmonics of this RF signal might mix with the harmonics of the LO, and the mixing product of these two undesired signals can fall into the IF frequency band, which is again an interference and should be avoided. So let us take an example. So you have an FRF of 2.4 gigahertz, you have FLO of 3 gigahertz, and the desired IF is 600 megahertz. And now if I take M and N as 4 and minus 3, you have 4 FRF minus 3 FLO, you get a signal which is exactly equal to the IF frequency, which is totally not desired because it overlaps with the desired signal which is produced by the input of 2.4 gigahertz. That is why it is very important to have very good spurious response, in a sense that the spurious products that are generated are very low compared to the desired IF output. So let us review the mixer fundamentals that we have discussed so far in this lecture. So a mixer is represented using this symbol. It has 3 ports, RF, LO and IF, and the basic mixer operation is, if I have two frequencies at the RF and LO, F1 and F2, ideally I get F2 plus F1 and F2 minus F1. If I choose the sum frequency, it's called as up conversion process or up conversion mixer. If I choose the difference frequency, the process is called as down conversion or a down converter mixer. The mixer can be implemented using a diode, BJT, FET as a nonlinear device or as a switching device. And if we implement the mixer using these things, what we actually get, so this is the ideal output, what we actually get is this, and these are the mixer non-idealities or specifications or mixer performance matrix, which are nothing but conversion gain, port to port isolation, noise figure, linearity and spurious response. So these are the things that we discuss in this lecture. In next lecture, we are going to cover the devices that we use for mixers, which are diodes and transistors. We will see how those function as a mixing devices, and then we will also discuss the analysis of various mixer circuits that are used to implement mixers. Thank you.